So dear students, in this video we are going to calculate the electric field due to a dipole at any point on its axis. Dipole at any point on its axis. So these points are also known as axial points. Okay, so you already have an idea about what dipole is. It is basically a system of charges, equal and opposite charges, separated by a distance of 2a. Let O is the center of the dipole, such that these distances are AH, and there is a dipole moment vector associated with this dipole, which is directed from negative charge to the positive charge, and which is indicated by P vector. Now consider, so this is your dipole or a dipole system. Now consider any point at its axial line. So the dotted line represent the axis of the axis of a dipole. So I want to indicate any point P at the axis, which is let the distance of r from the center of the dipole. Now our intention here is to calculate the net electric field at point P due to the dipole system. So for that we are going to utilize superposition principle, which tells us that the net electric field at point P will be the vector sum of the electric field at point P due to positive charge plus the electric field at point P due to the negative charge. So firstly we are going to calculate the electric field at point P due to positive charge, that is E plus Q. So E plus Q will be equals to 1 by 4 pi epsilon 0 Q divided by, now the distance from the point charge Q to point P is, from here to here the distance is A, and from here to here the distance we are going to calculate. So here to here the distance is R, and here to here the distance is A. Therefore from here to here the distance is R minus A squared. And at point P, due to this positive charge, the direction of the electric field will be outward, this way. At this point, due to this charge, the direction of the electric field will be outward, and this outward direction can be indicated by the direction of the dipole moment unit vector itself, because the dipole moment vector is also directed towards the same direction. Similarly, E minus Q, the electric field at point P due to negative charge, will be equals to 1 by 4 pi epsilon 0 Q divided by, now the distance from here to here is this distance plus this distance, so that will be equals to R plus A whole square. But the direction of the electric field at point P due to this negative charge will be towards this directions, that is towards the charge itself. Now this direction is opposite to the direction of the dipole moment vector. That's why the direction of this electric field may be represented by minus P vector. Now the net field due to the whole system at point P will be the vector sum of this and this. The net field at point P, that is EP will be equals to E plus Q, E minus Q. This implies EP will be equals to E plus Q, we have already calculated, 1 by 4 pi epsilon 0 Q divided by R minus E whole square, and the direction of the unit vector, directional unit vector, plus E minus Q is 1 divided by 4 pi epsilon 0 Q by R plus A whole square minus P vector. This implies EP is equals to 1 divided by 4 pi epsilon 0 Q divided by R minus A whole square P, now plus P, now this plus into minus will be minus here, so 1 by 4 pi epsilon 0 Q by R plus A whole square, only P is remained here. Now taking the common terms outside, we'll have 1 by 4 pi epsilon 0, okay, Q can also be taken outside, so Q by 4 pi epsilon 0 1 divided by R minus A whole square minus 1 divided by R plus A whole square P vector. Now you have to solve this terms inside the bracket. So this will give me Q by 4 pi epsilon 0. So the LCM of the two will be R minus A whole square into R plus A whole square, and R plus A whole square goes this place and R minus A whole square goes this place, P unit vector. Okay, now this implies EP will be equals to Q divided by 4 pi epsilon 0. So when you solve this one, okay, I want to do, okay, let's do it here itself. So this is R square A square plus 2RA A plus B whole square minus, now this is in the form of E minus B whole square, so this will give me R square plus A square minus 2RA divided by, okay, let's keep this as it is for a moment. This gives EP is equals to Q divided by 4 pi epsilon 0 R square plus A square plus 2RA, so minus, multiply it by minus, you'll get this one. This minus multiplies this terms to get this terms, and okay, let's keep this as it is for the time being. Okay, here this R square get cancels with this R square, and this A square cancels with this A square. So this implies EP is equals to Q divided by 4 pi epsilon 0. So 2RA plus 2RA will give me 4RA divided by, now you break this terms, this is in the form of E minus B whole square and this is in the form of A plus B again. So this will give me R square plus A square minus 2RA into R square plus A square plus 2R. To P unit vector. this implies EP will be equals to Q divided by 4 pi epsilon 0. So now multiply each term of this bracket terms with each term of these bracket terms. So firstly, I'm going to multiply the each term of this bracket with r square. So I'll get r square into r square, r to the power 4, r square into a square, r square a square, r square into 2ra, 2r cube a. So r square is done. Again a square into r square, a square r square, a square into a square, a to the power 4, a square into 2ra, 2r a cube. So a square is done. Similarly, minus 2ra into r square is minus 2r cube a, minus 2ra into a square is minus 2ra cube, and minus 2ra into plus 2ra is minus 4r square a square. So some terms get cancels here. So the terms are 2r cube a, 2r cube a, 2ra cube, and 2ra cube. So the remaining term can be written as EP is equals to Q divided by 4 pi epsilon 0, 4ra. So r to the power 4, it is taken. Then a to the power 4, it is taken to r square plus a square. R square plus a square will give me 2r square a square. So these are taken, and the remaining one is minus 4r square a square p vector. So EP will be equals to Q divided by 4 pi epsilon 0, 4ra. So r to the power 4 plus e to the power 4. This will give me minus 2r square a square p vector. Now EP will be equals to Q divided by 4 pi epsilon 0, 4ra, 4ra divided by, so this can be written in the form of r square minus a square to the power square. I have written this term in the form of a square minus b square whole square. So is that this is r square square, that is r to the power 4, and so on. Now since our dipole is very small, so this a square can be neglected with respect to this r square. So that there is one consideration which is known as small dipole consideration, in which the dimension of the dipole is very small with respect to the distance of the axial point. Therefore, this distance of the axial point will be much more than the dimension of the dipole. So r is much greater than a. So this will give me EP is equals to Q divided by 4 pi epsilon 0, 4ra. So when you neglect a square with respect to r square, so it will be r to the power 4 p vector. Now this 4ra can be written, so this term in the numerator 4ra can be written in the terms of dipole moment vector. So EP will be Q divided by 4 pi epsilon 0. So 4ra can be written in the form as, if I inserted Q inside, so it will be, okay, firstly this r and this r get cancelled, r and the power, fourth power get cancelled, so I'll get Q inside, okay, not Q, will be just 4a divided by r cube p. Then EP will be equals to q divided by 4 pi epsilon 0. So if I put this q inside, it will be q into 4a divided by r cube with p vector. Then EP will be equals to 1 by 4 pi epsilon naught, because I have already inserted q inside. So q into 2a, we already know that quantity, so q into 2a will be your dipole moment. Now 2 is left, so 2 into p, where p is your q into 2a. It is the magnitude of the dipole moment divided by r cube with dipole moment vector. Now this dipole moment magnitude and dipole moment's unit vector will give me the dipole moment vector itself. So EP is equals to 1 by 4 pi epsilon naught. So this 2 comes here. So this is your p vector. Since p will give me p vector. So p vector divided by r cube, or EP is equals to 2p vector divided by 4 pi epsilon naught r cube. So this is your electric field, the value of the electric field at any point on the axis of a dipole. Any point. If this point is here, then even the relation of electric field will not change. At this point also, the direction of the electric field will be towards the direction of the dipole moment vector. So in general, we have derived the relation of electric field due to a dipole at any point on its axis. And we have to note one thing here, and that is the direction of the dipole moment vector and electric field at any point on the axis of the dipole are always same. Thank you.